All right, so next let's derive the mole balance for the batch reactor. So again, before we do that, let's go to the University of Michigan Equipment Encyclopedia and see what a cartoon for a batch reactor. In this case, just like the CSTR, we have two things enter, a blue and a yellow. They empty into the batch, fill up. We get a pink, a well-mixed pink. The reaction proceeds, and then once the reaction is over, the tank drains. So how does the batch reactor work? So basically, the batch reactor is filled. The fluid inside the reactor is then well mixed. Reaction is carried out. Once the reaction is over, the reactor is drained. So how does the batch reactor work? Step one, fill the batch reactor. Step two, mix it up. Three, carry out the reaction. 4, drain. There's another step here, clean, and then repeat. So basically in a batch reactor, you're making batches of stuff. So you make one batch, drain it, clean it out, add the ingredients, mix it up, carry out the reaction. There's your second batch, drain it, clean, repeat. So one consideration to make when you're designing a batch reactor is that you have to take time to do all of these things. You have to take time to fill, you have to take time to mix, you have to take time to carry out the reaction, you have to take time to drain, and you have to take time to clean. When we solve mole balances, the only thing that we are doing is determining the time needed to carry out the reaction. So keep this in mind. When you design batch reactors, there's a bunch of other times that you need to take into account. And there's actually a table in Fogler that gives estimates for the remainder of these processes. But we'll get to that later in the class. For now, let's derive the mole balance. So first, what are the key assumptions to the batch reactor? Well, one is this, just like the CSTR, it's well mixed. And that's important because that tells us how to write our reaction rate. The other is no inflows or outflows. So even though we have to fill the reactor and we have to drain the reactor, when the reaction is taking place, there are no inflows or outflows. So we are writing the balance over the batch reactor when the reaction is taking place. And at that time, we don't have any inflows or outflows. It's a batch system. So taking these assumptions into account, we can write down the mole balance for the batch reactor. The batch reactor, it does not operate at steady state, so we cannot cancel out the accumulation term. So that has to stay, dNA dt. However, there are no inflows or outflows, so the flow rate terms, the flow terms, those don't come into play. Now we just have the reaction rate, so the net generation consumption term, which in this case, for the well-mixed case, is going to be RA times B. For the special case where we have a constant volume batch reactor, that means that this quantity doesn't change over the course of the reaction. This is a constant. So one thing that's convenient to do is to combine this volume term with this N term. So if you recall, this N term is for the number of moles, so the number of moles of A. So if I divide both sides by volume, then volume on this side goes away, and on this side I have Na, the number of moles of A, divided by the volume of A, which is the concentration of A. So that's convenient because the rate is usually written in terms of concentration. So that means that I put everything into one consistent variable right there. So let's do that. So for the special case where I have a constant volume batch reactor, I can say dCA is equal to Ra. And that's it. There's the mole balance for my constant volume batch reactor.